Good morning and welcome everybody to episode 22. 22, that's quite a lot. Of the MakerBot Chats. My name is Felipe, I'm your host. As usual, it's great to have you guys all here again. Welcome back to my living room, my printing area. It's always nice to share this with you. And today we have quite an interesting one because we've received a few comments in the past about you guys wanting to know more about Sketch in specific. Lately, we've focused many of our chats in our method platform, which is amazing for more materials. I couldn't talk enough good stuff about it, but we haven't focused as much in our our Sketch platform, which is our more EDU tailored platform. It's not necessarily to say that it's a limited printer. It's just the idea behind it is that it's a system more focused in prototyping, in experimenting. I just want to confirm that things are running smoothly. Can you refresh? For some reason, I've been having issues like just getting the stream started. I don't know, like there's something going on with the stream key, but I think it's running now. So just let me know in the comment section if you see anything, if you get our stream right now. But in any case, going back to our Sketch platform. So as I was saying, it's meant for, let's say, well, basically one material, PLA. You can also use TUF with it, but it's tailored for PLA. It's amazing for simple prints. You will not be able to use the dual print settings that you have, generally speaking, with the method. With Sketch, it's kind of like a little bit more, it's single tool, single job, but it does that amazingly well. It's really efficient at what it does. And I just want to show a little bit more of the specific things that you could do. And today we're going to be talking about gears. I've been working on a project for a while now. I think that some of you may have seen it from past episodes. It's a gear, a mechanical gripper, right? As you can see here, this one was printed on the method. It's on nylon carbon fiber. However, as I've been iterating on it, and it's actually, it's taking a few different iterations. So this was the original one, which I actually printed on the Sketch. And the reason why I bring this up is because I want to talk today about my process when using the Sketch, why I use it, and specifically how do I use it for printing some of the smaller components that will run these types of robots, right? So today is all about gears in the Sketch, best practices, how to model them. A little bit I'll touch on that. As you know, my modeling tool of choice is Rhino, but many of the things that I'll be talking about apply for the general variety of modeling softwares that you could be using. So I'll start by showing you some, let me switch back here, some of my iterations with my gears. So as you can see, I have quite a few printed examples, from the very beginning, my very first tests on what I was doing. This is what's called a planetary gear system. It's also kind of like a high torque planetary gear system. And the way that it works, it's actually trying to transmit the rotational force of a motor through into a second component. So here I have my final assembly. I'll talk about it more in detail in a second. But for now, let's just focus on the components of it, right? As you can see, there's, I would say, three main gears, right? You have the main sort of outer rim for the planets. The reason why this is called a planetary gear system is because, as you can, as the name suggests, you have some sort of sun, right? A centerpiece of a center gear. You have the planets that will orbit the sun. So as you can see, as I spin the planets, and just the caveat here is that this was one of my first attempts at actually printing this gear. So you can see how it's not as smooth as you'd want it to be. I had to troubleshoot some of this. I had to play a little bit with the tolerances. And that's what I'm going to be describing today. That's what I'm going to be showing you guys today. What were the tolerances that I used? What are the problems that I encountered? But again, I've got my sun. I've got my planets who are supposed to orbit that sun. And I have my outer rim, which is the final piece that will allow my planet and suns well, my planets and sun to rotate around that specific pattern. Let me try to bring it back in. And I think, you probably can see from now some of the issues that I encountered early on when printing this. So I'll start by talking a little bit about those and then how did I compensate for them. As you can see, it's fairly hard for me to slide the planets into the orbit element. The reason is not necessarily because of the offset. So as a general rule of thumb, and you probably have heard me say this before, I try to use a 200 micron offset when I want, kind of looser tolerances. I'll take these planets as sun as an example, right? Here the tolerances are really, really loose, right? The planets are really easy to take out from the rods that are hosting them, right? So it's a 200 micron offset. In this case, I also have the 200 micron offset, but what's happening here, it's what's commonly referred to as, well, I've seen some people talk about it as elephant's paw. I think that the appropriate technical term here is actually over extrusion, right? So that tends to happen sometimes, especially with heated build plates, which is what the MakerBot Sketch has and uses. And what that means, what over extrusion, especially on the first layer, right, means is that you will be getting a little bit of an extra amount of plastic that sort of drips outwards from your print surface. I'll try to zoom in as much as possible. As you know, like this, the webcam, I think it picks it up fairly well, fairly okay. Let's see if I can make it focus into my hands. If I stop moving, will it? Maybe not so close. There we go. So as you can see, it's just those shiny edges, right? So those are edges that are actually going to be over extruded. The plastic is quite literally overflowing and peeling to the sides. That happens commonly in the first layer because the machine is sort of like pushing that plastic out into the build plate. And as it does so, as you can imagine, like as it squirts it out, it sort of pushes it outwards, right? There's many ways to compensate for that. The first one could probably be like the more obvious one would be to change your dimensions. I think that that's not ideal because of course that's going to alter how your system works. The better way to do it actually, and I'll show it with the second print, is to chamfer some of those first layers, right? We could debate a little bit of whether you're affecting or not the design here, but I think it's kind of part of the limitations that come with the process that are really important to understand. So with any given process, whether you're using 3D printing, injection molding, wood cutting, you name it, right? There will be limitations on what you could do and what's kind of like the best practices, how to get the most out of your machine. Specifically in this case with 3D printing and with heated build plates, what's happening is that you're just better off with having a little bit of a chamfer in the first layer because that will essentially avoid or eliminate the issues that come with said over extrusion or elephant's paw. So this was my first iteration at these gears. I'll go into Rhino in a second, but just so you know, kind of like how did the design evolve. Here I have a very similar, I changed the size of the gears a little bit. The reason was, let me put this in. You can see how it slides much more easily in the second iteration. I changed the size of the gears, so I basically inverted the size of my sun and the size of my planets here. The reason being I wanted to have like a higher torque ratio. So if you imagine when you're doing, when you're using your bicycle, right? If you have a small gear, drive a bigger gear, you're going to have basically high speed transform into low speed, and that in turn increases your torque. In this case, I would have a big gear spinning a small gear, so essentially speeding up my revolutions, but I would probably be losing a lot of torque, a lot of force in doing that translation. So by inverting them, I actually have a little bit more force. I'm able to maintain the torque that the motor is giving me and even multiplying it a little bit more, which is what I'm trying to do because of the type of assembly that I'll be working with. In any case, here what you see, in my second iteration is I started, and I'll try to zoom in again into it. So I started adding these chamfers in all of my gears, right? So you can see it happening. Let's see if I can bring it a little bit closer. In Rhino, we'll be able to see it in much more greater detail, but you can see how these, the edges here in the first set of gears are completely flat, right? I basically just extruded the gears and called it a day. And after realizing that I was getting those issues with the over extrusion on the first couple of layers, I just went ahead and chamfered both sides. And this was mainly for aesthetics. You don't necessarily have to be doing it on both sides, but I wanted them to be sort of to have the same looks on both sides. So I went ahead and chamfered both elements, the top of the gear and the bottom of the gear. And that essentially gave me enough room, and you can see how it wiggles even a little bit. I could try to make it a little bit tighter, but enough room for my gears to play along nicely, to be able to spin along nicely, and ultimately to deliver the results, which is what I have here in my final assembly that I was looking for. On my final assembly, I will be having an NEMA 17 motor. It's powered by a Raspberry Pi and just a kind of an Arduino hat that's provided by Adafruit. But yeah, NEMA 17 into my planetary gears, and I'll talk about the assembly in a second. But before we go into the assembly, I want to show you more on, what I actually did in Rhino as I was modeling this out. So this might be an easier way for us to talk about and to see what was happening in the initial iterations. So as I was iterating here, it's kind of difficult to orbit without my mouse here, but in my initial iterations, right, a couple of things to note. I was playing with the amount of teeth that I had in the gears. I was also playing with the number of gears, how many planets did I want to have. As long as you don't have, as long as the planets don't touch each other, you can have as many planets as you want. It's going to add a lot more friction, but it also, sort of the balance that's happening here is that the more planets you have, the more centered your sun gear is going to be, but also the more friction you will have. And as you can see here, initially kind of my first iterations were around large sun and smaller planets. So that would be optimizing for speed. Essentially, I'm having the sun rotate once and the planets will rotate multiple times, which in turn decreases my torque but increases my speed. You guys can correct me if you think that I'm wrong. I'm sure that I could use some tutorials on torque and gear ratios, but I know some from, I like cycling a lot, so that's where I get most of it. In any case, sorry for that weird tangent, but second iteration, right, as I started to focus on, maybe the right amount of planets is just 3, because that gives me enough control of the planets and enough control of the sun. It'll keep the sun in a fixed spot. As I was saying, the more planets that you have, the easier it is to sort of locate your sun. Not necessarily because of the, they will, all of the planets and the sun will be sort of fixed by, stems and the motor itself and the shafts. But if you can see here, here in this just curved diagram, if you can imagine, and I know that these shapes overlap right now, but if you imagine me having just the 2 planets and the sun in the center, it's going to just be tricky for me to keep that consistency happening, especially if I don't have really tight tolerances, which are hard to achieve with some of the thermoplastics, right? As they wear out, as they turn around, you can have some issues with that. So adding an extra planet on, narrowing it down to 3 planets and 1 sun gave me enough control over what I wanted So basically keeping my sun centered in my assembly. And at the same time, it was something that I could, I was able to easily iterate on. And as you can see here, this is the first time that I started adding the chamfer into my outer rim for the planets. And, I noticed how much it helped in the outer rim. Initially, I was doing it just because I wanted me, to be able to slide the planets in and out much easier than what I was doing at the beginning. But after iterating a few times, I realized that, it just made a lot of sense for me to focus on that chamfering of the edges. And for the final iterations, as you can see here, I have my larger planets, my smaller sun, and my outer rim as well. All of them now present that chamfer edge, you know, both on the top and in the bottom of the shape. This is an easy feature to do in Fusion and Rhino. Essentially just extrude your cylinder and then chamfer those out to make sure that you have enough space between the gears. As I said before, let's talk about, now that I'm mentioning the space. Sorry. The space that I was using, the offset that I was using between my parts was roughly 200 microns. A little bit more, right? It depends, as you can see here in my top view, it depends on the specific component that I'm referring to. But overall, here, let's see, align dimension. I've got my, my perpendicular dimension. So yeah, 260 microns, and it's going to be a little bit more here in the offset from my planet to my outer rim. It's almost 0.5 millimeter. The reason for that is that you really don't want those teeth to be sort of completely interlocking with the outer rim or with any other gear for that matter, because that is going to prevent them from spinning smoothly, right? That's something that sort of you have to play and work and see depending on the sizes that you're using. But I would say, as usual, the rule of thumb for cylindrical offsets, kind of 100 microns to 200 microns for a loose and smooth axis. In the case of the gears, I would double it a little bit, so go to 200 to 400 microns depending on the specific size of the gears. And the final tip to use there is actually to go ahead and always try to chamfer the base of your parts and of your gears, because that is going to allow you, or to prevent you from having any issues with over extrusion, with that sort of elephant spot that people call. And you know, if it's not sort of an aesthetic detail that you mind about, if you don't mind having like that extra feature on your part, it's a great way to just simplify things for you. I'm going to go ahead and jump into MakerBot Print and show you, where's my MakerBot Print? You know, what happens once I start importing those parts into my MakerBot Print. So I have, first of all, I have two build plates here. One just shows my, let me hide this project. One just shows my gears. The other one is going to show my outer rim, like that's housing the gears. And as you can see, I'm able to export the gears in a single go. So what I did here from Rhino, I just exported all of the gears as a single STL, and you know, MakerBot Print just interprets it as a single geometry. Once I have them in MakerBot Print, I don't really mind, you know, the proximity between the gears. That's one other thing to keep in mind, especially if you're exporting multiple geometries together. Just make sure that they are at least 0.5 millimeter from each other. Otherwise, you do risk having a little bit of stringing between the parts. This is something that, you know, it's not necessarily something that MakerBot Print will tell you, unless you're exporting something a little bit closer to, I have a good example here, something that will autoplate in your build plate. So this is a different study that I made some time ago. It's actually the fingers for this gripper, right? So what I have here are the fingers. And as you can see here, this plate was actually autoplated from my assembly, right? So it all depends. You know, the offset that you will give to your parts can either be auto-calibrated by MakerBot Print, or it can be manually created when you export that STL. If you're exporting an STL, MakerBot Print will not sort of interpret the individual geometries and place them in a sort of optimal position. It's taking the STL as is. It's taking, as you can see here, it's taking my gears exactly as I exported them from Rhino. It's not moving them around, so you know, you're pretty much set on where they are. Even if I click on them, they all behave as a single element, right? They are going to be moving around as a single element in my build plate. So just keep that in mind. When you're exporting your files, especially if you're using an STL file, just remember that if you have an assembly, if you have multiple components there, the distance between your components is going to be static once, or set once you bring them into MakerBot Print, right? But as long as you have more than 5 millimeters between the components, you should be fine. So this is actually the way that I printed my gears. I had no issues here. It's probably a little bit more, maybe about 1.5 millimeters there, and maybe the closest they get is about 0.5 millimeter, but that's completely fine, right? You just don't want to get them too close. So this is borderline edge case of what you want to do. And then from there on, the other really important thing to ask yourself is whether you want to use a raft or not. One of the great things about Sketch is that you actually don't need a raft necessarily because you're using a build plate. The raft is essentially going to print an extra layer of plastic before your part gets printed. And I actually can slice it for you guys here so you can see. But it's actually generating sort of an additional pseudo build plate, if you want, that will make sure that all of your parts start from the same level. With Sketch's build plate, it's really flat, it's really straight. It's more a matter of what are you trying to print. That's what should drive your decision when choosing. Well, two things. What are you trying to print, and what's the time that you want to spend printing, right? In this case, because I've already changed so many components to make sure that first, or so many settings to make sure that first layer is really perfect, flat, and it doesn't have any issues with over extrusion, that elephant spot that we were talking before, I really don't necessarily need the raft, right? As you can see, the raft is my yellow element here that's going to be printed prior to my gears here. I would say that the raft is better suited for something that is not, if say you don't want to use that chamfer edges on the sides or around your parts like what I'm doing here for the gears, and you just want a straight on edge, you will have better control over that over extrusion of the first layers if you're using a raft than if you're using, if you're printing directly against a build plate. Why? Because the first layer, when printed against a build plate, it's going to have, the printer will just try to force itself a little bit more to make sure that first layer really adheres to the build plate, right? If you're using a raft, there's going to be, and you can control that, there's going to be an offset between the raft and your first layer. That will in turn diminish the effects of over extrusion for the first layer, and it might help in a similar way than that chamfering does. In my case, I just felt that it worked just better chamfering the edges for the gears, because it's not only about that first layer, it's also about how do the gears interact with each other and how smoothly they can interlock with each other. So you can go ahead and try it, test it. But I would say my take for specifically, and today that's what we're talking about, specifically for gears, you're better off with just chamfering the edges of them all just to make sure that you have a smoother transition and you avoid any issues with over extrusion. That also will avoid the need for, or override the need for using a raft, and instead you can just print directly against the build plate. So I could go ahead here, and instead of, in my base layer, I could just choose none. Oh, and by the way, you'll see how much it affects your print time, which is also an important thing to note. So with the raft, I'm at about 59 minutes. Since it's a small print, it might not be a big change, but let's see, it should be noticeable. So let's click none, slice it again. It's going to take a few seconds to slice. But it should go down, like from those 59 minutes, it should go down, I'm guessing, like to 45, 48, so about 10 minutes, but we'll see. So as you can see, yeah, 47, right? So as you can see, my raft is not present anymore because I disabled it. So the gears are going to be printed directly on my build plate without any further need of material, right? And so far it's worked great. It actually allowed me to ease a lot of the tension, or in the interaction of my parts. So it worked amazingly well. And now I'll go ahead and you guys can start sending your questions in the chat section to the right. But I'm going to go ahead and also show you guys the final assembly. And it's kind of building. And let's see, can I actually? Well, you won't see my face here. But it's kind of building towards a larger robot project that I'm working on, that I'm hoping to share with you guys in the coming weeks. But what I want to show is actually the motor running, so that you can see you know, in the final assembly, what's the end goal and how do these planetary gears actually interact with each other. So I'll just go ahead and run my Python script in my Pi. I'll just put it there in the script. So as you can see, I'm using the NEMA 17 motor to do a few revolutions one way and a few revolutions the other way. The reason why I created this assembly and the reason why I'm using these planetary gears is because I'm actually building a shaft to house my gripper. So I'm adding some more, you know, motion elements to my gripper. So this is my original gripper that you may have seen in previous chats episodes. The gripper itself is also actuated using a NEMA 17 motor. So as the motor spins, the jaws open and close, right? The NEMA 17 motor is housed in this element, and in turn, this element actually is nested up against the planetary gears, right? So once I have the final assembly, and I won't completely push it through, but the idea is that this secondary motor that you can see here is what's going to be driving the rotation of my gripper. So I'll run my script again. As I said, I'm using just a Python script on the Raspberry Pi. But as you can see, you know, the motor spins one way, spins the other way, and that's what's going to become essentially the wrist rotation of my gripper here, right? It's going to take a few more takes, I'm thinking. But that was the idea, and that was also why the reason behind using this sort of high torque, low speed ratio on the gears, because I really wanted to make sure that the NEMA 17 motor is going to have enough strength to rotate that hand, that gripper, even when the gripper is fully loaded, right? So you can assume that, or you can imagine how, as I'm starting to add weight on top of the motor, it's going to require more force to drive that assembly. So I'll just run it again because I really like running it. Runs one way, and I'll be able to control that, right? The amount of rotations. That's also why I'm using the stepper motor. It's going to give me a lot more control. I can actually count the steps, basically the amount of, how should I say it, arc sections that this motor is going to be spinning, and that will allow me to control my, here we go. It will allow me to control my final assembly. So really excited about that one. I'm going to go ahead and start jumping into your guys' questions. But yeah, all in all, you know, that's kind of the big takes for the gears. Let's see. How can I get a solid infill on small gear features? That's a good one. So if I go back here to MakerBot Print and go back to settings, and this is true for any type of print, right? You can try and do 100% infill. So here you will see the infill setting. If you don't see it, which I don't think it's possible. Oh no, you're actually able to hide it. I'll bring it back. Well, I'll actually hide it just to show you guys how to expose it, and then we'll talk about how to change it. So if you go back, starting from scratch, go to print settings here in MakerBot Print, then go to custom settings. And here you will see the infill element. In the infill, you will be able to see infill density, and just click show. You can maybe not show it and change it from here. I think it's just better to have it exposed constantly. And then the infill density is just going to ask for you for a percentage of infill, right? So how solid do you want your parts to be? And in Sketch, in the case of the Sketch printer, you can just go ahead and hit 100%. It's going to say 95. That is as close as you'll be able to get, and I'm going to reslice it, and you'll see the difference that it makes to a solid infill. With Sketch, you can only go to 95. That essentially is completely solid. There's not much more room left for you to put material in. However, if you're using our method platform, you're actually able to choose solid infill, right? In the method, you can actually slice for a solid infill, and that will actually ask the printer to fill up any of the gaps, any and all of the gaps that you might have inside of your parts. So as you can see here, my parts are pretty much filled up. The reason why it's not actually accessing the insides of the teeth is that because it's already like 2 walls, and actually 4, because if you think about the 2 sides, 4 walls, and the inside of it will only cause issues and over extrusion if you force the extruder through. So that's how you can get solid infills in small gear features. How to calculate the ultimate torque for a gear? That's that's not a question for me, and I would actually have to get into the physics of it. It essentially involves calculating how do the gears radius relate to one another, and depending on the number of gears that you have connected, that's going to change. It's definitely not a subject for today. It's not that complicated, right? But it's just calculating the torque based on the radius that the gears share and how they are connected, whether it's going from a small gear to a large gear or from a big gear to a small gear. What are the optimal materials for plastic gears? That's a good question, actually. And I would say that, if you're using some simple robotics experiment, if you're using something, if you're doing something like what I've just shown you, PLA should be fine. I would also say that tough can work really well, especially because it sort of has this chewy property to it, so it's going to be able to withstand a little bit more of the wear and tear of the gears as they spin. Personally, I would recommend nylon as the ideal material because it's really good at resisting repetitive forces. It's also good with abrasion. Unfortunately, you cannot use nylon with the MakerBot Sketch, but you can use it with the MakerBot method, right? So it all depends. For more advanced applications, nylon would be my go-to material. If you're just doing something a little bit more basic and it's not, not necessarily an industrial application, PLA and tough would be perfect and fine for that application. Do I need support structures when printing articulated objects? The answer, as usual, is it depends. So, for example, in the case of these, let me bring my camera back in here, and we're a little bit running out of time. But, sorry. Here we go, main camera, fading. This assembly was not printed in a single go, right? So I split the assembly into multiple components, and I printed each component individually. So it all depends, for each component, will you need supports or not? It depends on the component. Even with the most complex component, which is the main hub of my gripper, I didn't use supports. I was, able to get away with that. It all depends on the specifics of your geometry. Do I need to adjust the filament diameter? No, and you cannot adjust the filament diameter. So both MakerBot Sketch and MakerBot Method are going to be working with 1.75 millimeters in diameter, and you're not able to use anything bigger or smaller than that. Do I need to match the extrusion width with the wall thickness? The extrusion width with the wall thickness. I am not sure I understand that question. Do I need to? I'm assuming that you're talking about the nozzle width to the wall thickness. That is actually a good idea. With MakerBot Print and when using the MakerBot systems, it's sort of taken, the printer itself knows what to do. But generally speaking, so it's actually a nozzle width. Okay, so the question is, do they need to match the extrusion width with the wall thickness? Yes, that's a very good idea. Generally speaking, all of MakerBot's printers will have a nozzle diameter of 400 microns, and that's also what we use to calculate the wall thickness. And actually, we tend to default to 2 walls when printing, and that's the best way to calculate it. So, the width should match, the nozzle diameter should match your wall thickness. It also is important to think about the layer height when doing that, but that's a little bit more of a technical, definitely it's something that we could look into, right, in future episodes, but more of a technical question. Can I print more than one assembly at a time? Yes, 100%, like kind of what I was showing here with this. It's not yes, you could print more than one assembly. I wouldn't necessarily recommend printing nested objects, right? So it all depends on how complex that assembly is, how big the assembly is, but you can definitely print multiple objects in a single go, at once with Sketch. That's one of the great things about that heated build plate, which I really, really, really like. But in any case, I think we're running out of time. You can still, keep pushing those questions up in YouTube. We'll try to answer as many of them as we can. Or you can also reach us at hello@makerbot.com, Felipe, Felipe, at makerbot.com, with any questions, comments, and ideas that you might have for future episodes. But for now, I'm actually going to say goodbye. Happy printing, and I'll see you next time. Thanks again. and have a good week.